We've all heard it, nothing can travel faster than the speed of light. That number, a blistering 670.6 million miles per hour, is the ultimate speed limit for the entire universe. But have you ever really asked why? What's actually stopping you from putting the pedal to the metal and flying right past it? Is there some cosmic traffic cop hiding behind a nebula, waiting to pull you over? The typical answer you hear is that it would take infinite energy to get there. But that's not really an answer, is it? It's just a symptom of something much deeper, and much stranger, happening to the very fabric of reality. The real reason is built into the nuts and bolts of the universe. It's a fundamental rule that links space and time in a way that, thanks to thinkers like Einstein and Richard Feynman, will completely reshape how you see the world. Because the speed of light isn't just about light. It's the speed of reality itself. The first cracks in infinity for most of human history, the speed of light was basically infinite. It seemed obvious, you light a candle, and the room is bright. Instantly. How could you possibly measure something like that? Early attempts were pretty clever, like Galileo's idea to have two people with covered lanterns on distant hills. One would uncover his, and the second the other person saw it, they'd uncover theirs. But light was just too fast. Any delay was impossible for a human to notice. The first real breakthrough came in the 1670s, not from an experiment on Earth, but by looking way out at Jupiter. The Danish astronomer Ole Rømer was carefully tracking the orbits of Jupiter's moons. He noticed something odd: the timing of the moon Io's eclipses seemed to shift throughout the year. When Earth was moving away from Jupiter, the eclipses happened later than he predicted. When Earth was moving towards Jupiter, they happened a bit earlier. Rømer had a flash of genius. It wasn't Io that was messing up, it was the light. The news of the eclipse was taking longer to get to Earth when we were farther away. He had just proved that light has a finite, measurable speed. It was a discovery that changed our understanding of the cosmos forever. But the story got even weirder in the 1800s. The physicist James Clerk Maxwell was piecing together the laws of electricity and magnetism. He managed to unite them into a single, beautiful set of equations. And buried inside that math was something nobody expected: a speed. His equations predicted that an electromagnetic wave, a ripple in electric and magnetic fields, had to travel through a vacuum at a very specific, unchanging speed. When he calculated that number, it came out to be about 300,000 kilometers per second. This was the exact same speed that astronomers had measured for light. It was an incredible revelation: light is an electromagnetic wave. But Maxwell's equations also created a puzzle that would completely break classical physics. They predicted light speed as a constant, c. And this is the key part: the equations suggested this speed was always the same, no matter what. That simple, stubborn fact would lead directly to Albert Einstein. Einstein's reality-bending idea. This is where your everyday intuition has to take a backseat for a minute. Imagine you're on a highway driving 60 miles per hour. A car in the next lane zips by at 70. From your point of view, it's only pulling away at 10 miles per hour. Simple enough. Now, let's get on a spaceship. You're cruising at half the speed of light. You flip on your headlights. How fast does that beam of light move away from you? Common sense screams it should be half the speed of light. But Maxwell and, later, Einstein said no. You, inside that ship, would measure that light beam racing away from you at the full 670.6 million miles per hour. And here's the kicker: someone standing still back on Earth would also measure that very same beam traveling at the exact same speed. How is that possible? How can one thing have the same speed relative to two different observers moving at wildly different speeds? Einstein realized there was only one way this could work: if space and time themselves weren't rigid and absolute. If they were flexible, bendy things that could stretch and shrink to make sure the speed of light stays constant for everyone. This mind-bending idea leads to two major consequences. The first is time dilation. The faster you move through space, the slower time passes for you, relative to someone standing still. Think of a light clock, with a photon bouncing between two mirrors. For a person holding the clock, the photon just goes up and down. Tick, tock. But if that clock zooms past you, you'd see the photon travel a longer, diagonal path. Since the photon's speed is constant, and its path is now longer from your point of view, each tick must take more time. Time itself is literally running slower for the moving clock. The second consequence is length contraction. Objects moving at high speeds actually get squished in their direction of motion, from the perspective of an outside observer. These two effects, time dilation and length contraction, work in perfect harmony to keep the speed of light constant for every single observer. And this finally gives us the real answer to our question. Why does it take infinite energy to reach light speed? As you pump more and more energy into an object with mass, that energy increases its momentum. As you get closer and closer to c, you get less and less speed for your energy buck. The object resists changes in its motion more and more. To make that final push to reach the speed of light, you'd need an infinite amount of energy, because its momentum would become infinite. The universe itself structurally forbids it. So, we know it's impossible. But we're just getting to the heart of why. If your brain is melting in the best possible way, hit that subscribe button. Because what this speed limit truly represents is even more profound than just a cosmic red light. The speed of causality here's the biggest shift in thinking you can make. The speed of light is kind of a misnomer. It should really be called the speed of causality. Causality is just the simple idea that a cause has to come before its effect. You throw a ball, then the window breaks. For that simple logic to hold up, for reality to have a sensible sequence of events, there has to be a maximum speed at which any kind of influence can travel. There must be a delay between an event and its consequences, and that delay is governed by c. If you could send a signal faster than light, you could break the universe's logic. From certain points of view, you could send a message that arrives before it was sent. Effects could happen before their causes. The entire notion of before and after would shatter. So, this speed limit isn't just about travel, it's a rule that protects the timeline of the universe. It's the framework holding reality together. This is why physicists say c is more fundamental than light itself. Light travels at this speed in a vacuum because photons, the particles of light, have zero mass. Anything without mass must travel at this ultimate speed. But even if light didn't exist, this speed limit would still be woven into the geometry of space-time. It's the universe's fundamental exchange rate between space and time. Here's a powerful way to think about it. Imagine you are always traveling through four-dimensional space-time at one constant speed, the speed of light. Right now, as you're sitting still, almost all of that motion is through the time dimension. You're hurtling into the future. But when you start to move through space, when you walk, drive, or fly, you have to divert some of that motion from the time dimension into the spatial ones. You trade a little bit of your speed through time for speed through space. The faster you go through space, the slower you go through time. From this viewpoint, you can't go faster than light through space for the same reason you can't give more than 100% of your energy to something. You're already maxed out, always moving at c through space-time. For a particle like a photon, it dedicates 100% of its motion to traveling through space, leaving 0% for traveling through time. That's why, for a photon, time effectively doesn't pass at all. Proof in your pocket and in the stars. This all sounds like wild, abstract theory, but you use its real-world consequences every single day. The GPS on your phone relies on a network of satellites orbiting Earth. Those satellites are moving very fast, and they're also in a weaker gravitational field than we are. According to Einstein's theories of both special and general relativity, these factors change how fast their internal atomic clocks tick. Special relativity, their speed, slows their clocks down by about 7 microseconds per day, while general relativity, weaker gravity, speeds them up by about 45 microseconds per day. The net result is that the satellite clocks run faster by about 38 microseconds daily. If engineers didn't constantly correct for this, your GPS location would be off by miles every single day. The system only works because it accounts for a flexible, relativistic reality. We also see this limit enforced by the most powerful machines ever built. At the Large Hadron Collider, protons are accelerated to 99.9999991% of the speed of light. Scientists can pour staggering amounts of energy into them, but they can only get them infinitesimally closer to c, they can never, ever reach it. This isn't a failure of our technology, it's a confirmation of a fundamental law of nature. Perhaps the most elegant proof comes right from the sky. When cosmic rays hit our upper atmosphere, they create unstable particles called muons. At rest, a muon decays in about 2 microseconds, 2 millionths of a second. Even traveling near light speed, that's not nearly enough time for them to reach the Earth's surface before they vanish. But they do. We detect them down here all the time. Why? Because from our perspective on the ground, their internal clocks are ticking so slowly due to time dilation that their tiny lifespan gets stretched out, giving them plenty of time to complete the journey. So, 670.6 million miles per hour isn't just a big number. It isn't a speed limit for stuff. It's a basic property of the universe's operating system. It's the speed of cause and effect. It's the cosmic exchange rate between space and time. It's the constant beat that keeps reality from dissolving into paradox. The universe doesn't just have this speed limit. In a way, the universe is this speed limit. It's the structure that makes it possible to have a history and a future, a before and an after, a story that unfolds in an order that makes sense. It's not a barrier holding us back. It's the very rule that makes our existence possible. So here's a thought to leave you with: since all motion is a trade-off between moving through space and moving through time, where would you go if you could dedicate 99% of your universal speed to traveling through space? Let me know your thoughts in the comments below. And if you enjoyed having your reality bent just a little, like this video and subscribe for more deep dives into the rules of the cosmos.